bear with me for a moment. Imagine there's a train that goes half the speed of light, and you are standing on the platform, and there is a friend, let's name him X, on that train. Now, also the train has a headlight and everything, and it's dark, so you can see the headlight. Now, imagine from X's perspective, when the headlight is on, light is traveling at light speed, which is c, right? But X is himself traveling at half the speed of light. So from your perspective, technically, who you're standing at the platform, the light should be traveling 1.5 the speed of light, right? Since it's traveling its own speed, the speed of light, plus half the speed of light, because it's on a train, so it's traveling fast. So it should be 1.5 the speed of light. But that's not true, because light always travels at the speed of light. So, how is this possible? Let's take a look at that right now. Before proposing the general theory of relativity, Einstein had already drafted the special theory for relativity. It's known as a special theory because it applies to only special cases with insanely high speeds and time dilation and length contraction, that all of that which we can't see in our daily life, not even in our experiments. All of this are just thought experiments, right? So let's go back to the train example, okay? So, special theory of relativity. There is a Einstein was himself not satisfied with it because it does not apply to accelerating frames of references. Now, what is a frame of reference? I have a frame of reference, and X has a frame of reference. X on the train. So we can't have accelerated frames of references for this to work. So let's say that the train is moving at a constant speed. But if it is moving at a constant speed and I am stationary, then relativity says that there is no way I can distinguish between these two frames of references. The same laws of motion and laws of physics are going to apply to these both frames of references, and these are known as inertial frames of references. So now I just have this is the basic thing that has to happen. Okay, so there are two postulates when it comes to the special theory of relativity. The first postulate is that the laws of physics apply the same way to all initial frames of references. That is, if it is static, that is, if it is moving in a constant speed, that is, if it is not accelerating. The laws of physics apply the same way. And the second postulate is that the speed of light is the same. It will not change. Even if it is on a moving body that has its own speed, for any frame of reference, the speed of light is constant. Now, if that is to be true, we know that speed is equal to distance upon time. If speed is fixed, it cannot change, then that must mean that distance and time changes. And that's exactly what happens. These scenarios are known as time dilation and length contraction. How does time dilate exactly? Let's come up with an example. Let's go back to the train with our ex friend. If a friend X is holding a torch inside the train and there's a mirror on the other side of the compartment, so the beam of light goes towards the mirror and is reflected back towards X. For him, the light has traveled a straight distance, right? At a unit period of time. But X is moving in a train. From our frame of reference, we are on the platform. When X started the torch, the beam of light left the torch, and as it was moving forward, so was the train. So now it has carved out a path such as a V, or like two sides of a triangle. Now this path is considerably more than the path that X has himself recorded, right? Now how can this happen? See, the speed of light for me and X has to be same. It can't change. But the distance for me, from my perspective, is greater as compared to the distance that X has himself recorded. Now, if speed is same and the distance is greater, that means that the time has to change. Therefore, more time has passed from my perspective so that the light could travel a greater distance. That is known as time dilation. That means that from my perspective, X has slowed down, and that has allowed him more time and his light beam more time to travel such a large distance. As from X perspective, his time is going normally and his life is going normally. But this is known as relativity. This is known as different frames of references. Both are true at the same time. Both have the same laws of physics attached to them, but both have different results. The same of laws of physics. So, kaboom! That's wow! That's mind blowing, right? The same also happens with length contraction, but the length contraction is so small. It's like more than negligible. But let's take another example. If we take another example where the time is supposed to be smaller, and the time is supposed to go faster, and the length will contract. This is all mathematical. So this is the special theory of relativity, basically. That the speed of light is constant. That the difference between length and amount of seconds, that is space and time, is a very blurry line. And that means that space and time work together. Space and time are, we calculate space and time together. They are dependent on each other. And that's why we talk about a 4-dimensional universe with 3 dimensions of space and 1 dimension of time. And that is how special relativity opened us up to a whole new field of physics. Yeah, that was special relativity for you guys. Hopefully, I will see you soon. Bye bye.